So now we're going to start 9.1 after we introduce some preliminary that we did in the previous lecture videos. 9.1 we talk about the limit of sequences in Rn. So this is obviously similar to sequences in R1 where we have a sequence of real numbers. We talked about the meaning of the limit of this sequence, how do we find the limit, that sort of thing. So here we talk about a sequence in Rn. So here we use x, k. We use a vector notation here to be a sequence of points in Rn. So put it simply, xk is the collection of real numbers that has n components. So xkn. Where all those components are real. Okay? So it's a sequence. So this sequence converges to a limit point. Let's call this A. If so, this is very similar to limit of a sequence of real numbers. Give any epsilon, there exists a what? Think about that. There exists a natural number n such that when the subindex crosses the threshold, this implies the distance between xk and a. How do we measure the size of this? Well, which we talked about, we use norm to measure the distance here. Will be smaller than epsilon. B. So that's the meaning of convergence, okay? But obviously, to talk about this, we have to specify which norm that we're going to use. Next, a bounded sequence. So a sequence is bounded if and only if there is some constant m such that, think about what is less or equal to m for all k. For the real number sequence, I need to take the abs value of all the terms. It needs to be, finite. So here we take all the elements here. We're going to take its norm, okay? So that's the only difference, pretty much. Take the norm. C. Remember the Cauchy sequence? So here we try to define a Cauchy sequence in Rn. It's called a Cauchy sequence, or it's said to be Cauchy if so many of you probably already noticed this is so similar to sequence of real numbers. The only difference here is we have replaced the absolute value with the norm, okay, with the norm, because that's what we use to measure the magnitude or the size of points in Rn. Yes? So this is n, this is a little m here, okay? Cauchy sequence. So this part should not be too hard because we can easily extend what we know about real sequence to sequence in Rn. The following theorem explores connection between limit of a sequence in Rn with limit of sequence of R1, I guess. So let A be a point in Rn. In other words, it has n components. And xk be a sequence in Rn. So it looks like this. xk1, xk2, xkn. Then we say the limit of xk is a, okay? Then xk approaches a if and only if, well, each component, okay, this component approaches a1, this component approaches a2. So if and only if xkj, keep in mind there's no arrow here because this is a single component, it's a real number, approaches the associate component, which is a sub k or j. Alright, as k goes to infinity. If this is true for all j, j are numbers like 1, 2, 3, and all the way to n. And that's pretty easy to understand. So for example, if I'm talking about a sequence in R2, in other words, it has two components. Take this simple example for example, okay? So what is the limit of xk? What is the limit of xk? Well, to find this, according to the theorem, I just find out the corresponding components. I take this real number sequence and find out what happens when k goes to infinity. This obviously goes to 1 as k goes to infinity. And the second component obviously goes to 0 as k goes to infinity. And that's why we say, hey, the limit of this sequence in R2 is, that's the first component, that's the second component, is this point, okay, is this point in R2. So this can be easily extended to a higher dimension as well. So now, because of this, okay, because of this connection here, let me just simply say most results from R1 most results of a real sequence can be extended to Rn. Can be extended to higher dimension, okay, to higher dimension. For example, okay, the following theorem should be no surprise to everybody. Number 1, a sequence in Rn can have how many limit? At most 1, okay? It may not have any limit, in other words diverges, but if it has one limit, just at most 1. At most 1 limit. Number 2. If here we have a convergent sequence, then any subsequence. Think about what happens to any subsequence. So you pick infinite many terms randomly out of the sequence. Now, any subsequence also converges to where? To the same limit, okay? To the same limit or same point. Any subsequence also converges to the same point. Theorem number 3. Every that's wrong. Cross this off. Every convergent sequence in Rn is bounded. But obviously, not every bounded sequence is convergent, okay? So, but not conversely. Number 4, every convergent sequence must be a Cauchy sequence. Okay, it's Cauchy. You see how this is how similar this is to all the results that we already knew about. Okay, and that's why we're not spending too much time here, because like I said, a sequence in Rn is directly connected to the sequence in R1 because of all the components. Each component is a sequence in R1. So that's the 4th result. Number 5 is the most basic property. Like, how do we calculate the limit of the sum of 2 different sequences? One is given by xk, the other one is given by yk. They are both in Rn. Simple property. You just add up those 2 limits. All right, minus, minus. I can also take the limit of some scalar times by xk. So a scalar times by factor, you can just multiply each component with alpha. So you just take the alpha out, find out the limit of this. Now for real number sequence, okay, for real number sequence, you can talk about the product of 2 different sequences. But now we're talking about factors here, so you can only do the dot product. Okay, the dot product between 2 factors. You know, otherwise it's just does not make any sense. So how do you calculate the limit of a dot product? You know, which is going to be a real number. Okay, this dot product is a real number. Does it make sense to say, hey, you can just find out the limit of those 2 sequences? So this is going to be a factor. Do the dot product between those 2 limits. Okay, this is also pretty similar. All right, so these are essential properties. These are essential properties or theorems or results for sequences of Rn. Okay, sequences of Rn. None of them are surprising. Okay, none of them are surprising. And finally, we have the similar Bolzano-Weierstrass theorem. I want you to go back and try to review the Bolzano-Weierstrass theorem for a sequence in R1, and that's something we learned in analysis 1. Okay. Bolzano-Weierstrass theorem says every bounded sequence in Rn has a convergent subsequence. Has a convergent subsequence. Finally, did I already talk about this? I had a feeling I already talked about this. A sequence in Rn is Cauchy if and only if it converges. Okay, it converges. So this pretty much ends the most important properties for sequences in Rn. Okay, what we want to do next is to explore the limit of sequence with the topological structure of Rn. Remember the open sets and open balls that we talked about? So we're taking a little bit different approach here, okay? A little bit different approach. But otherwise, sequences in Rm behave pretty much the same as sequences in R. So now I'd like to look at things a little bit differently, okay? A little bit differently. So this is a theorem in your textbook. My version is the 4th edition, and this is the theorem 9.7 in the textbook. So here we're trying to look at things a bit differently. Given us a sequence in Rn, then xk converges to A. Remember a little while ago we had a theorem about what do we mean by, say, a sequence of Rn converges to A. That means each component converges to the corresponding component of A. Alright, that's what it means. But here we're trying to do it a little bit differently. So here we say xk converges to A if and only if for any open set containing A. There exists a natural number n such that any open sets such that if the subindex is big enough, such that if subindex is big enough, those points xk will eventually fall inside this open set V. Alright. So make a quick sketch, and pretty sure you can see this makes sense. So here we have a sequence in, let's say, just R2. Yes, on a piece of paper here. Let's say this limit approaches this point A. So that means for any open set V, that containing A, this open set V, eventually all the terms, okay, all those vectors or all those points will eventually be inside this open set. So when k is greater than n, greater or equal to n, let's say, they're all going to be inside here. Yeah. And that feels almost trivial, okay? That feels almost trivial. Geometrically, yes, it makes perfect sense. Here I like to provide a quick proof here so you can see the connection here, okay? Proof of this result. So first, let's assume xk converges to A. Think about what that means, all right? And let V be any open set. Containing A. Well, since V is open, that was given, since V is open, what does that mean? That means there is always a tiny epsilon such that there is an open ball centered at A with radius epsilon. Belongs to V, okay? Belongs to V. That's the meaning of openness. It's a subset of V. For this epsilon, there is an epsilon. For this epsilon, there is an n such that k greater or equal to n implies xk goes to A. So think about, where do I get this statement? This statement actually comes from the fact that x sub k converges to A, right? Converges to A. And that means for any epsilon. So right now I say, for this epsilon, there's an n so that the distance between xk and A will be smaller than epsilon. That's the precise definition of the limit, okay? So because of that, so this statement right here, okay, xk minus a less than epsilon. So this is equivalent to say the following geometric statement. This means xk, this point, belongs to this open set, to this open ball, which of course is a subset of V, as we know. Thus, this guy is part of V as well for k greater or equal to n. And that was what we're trying to prove. Okay, that was what we're trying to prove. So now, let's say the theorem was this, okay? Let's say for any open set V, there is an n so that xk is inside this open set. We want to prove xk converges to A. In other words, the distance is less than epsilon. Alright, so we want to prove the other direction. So now we assume for every open set V that has A in there, implies what? If you go back to the theorem, go back to the result, here, there's n, k greater than n, implies xk belongs to V. So it implies xk is inside V. So in fact, we may just choose, because this is for any open set, right? So we simply choose V to be, well, the open ball with radius epsilon centered at A. All right, so I'm going to replace this statement here with ball here, okay? Thus k greater to n implies xk is part of this open ball with radius epsilon. And what does that mean? All right, k greater to epsilon implies xk belongs to this. This is equivalent to say the distance between xk and A, well, measured by norm, is less than epsilon. In other words, the limit of xk is A. Okay, it's that simple. Okay, it's that simple. It takes some time to get used to a statement like this, but if you think about it, it's kind of a trivial, almost trivial. It's just the way we try to think this in terms of a topological structure of Rn. That's kind of tricky. And the last results I want to briefly mention before I wrap up 9.1. So 9.1 is a quick and short section on sequences in Rn. That's not really our goal here. Okay, our goal is obviously study functions in Rn. So our last results, which is theorem 9.8 in the textbook, it goes like this. And this is probably something we didn't see before. A set E in Rn is closed if and only if it contains all its accumulation point. So accumulation point is something that I will ask you guys to work on in your homework, so you understand what that means. It contains all its accumulation point. Let's think about what does that mean. Okay, let's think about what this statement means. Contains all accumulation point. That means for a sequence of points in E, and xk converges to x naught In other words, x naught is an accumulation point, right? X naught is an accumulation point. So x naught here is accumulation point. That'll imply, like what we said here, that'll imply accumulation point must be part of E, okay? That implies x naught, the limit of xk, the limit of any sequence in xk must be part of E, okay? Must be part of E. Now that's what this guy is. Let's take this set in R2, for example. In the usual sense, we have all the points inside along with everything here. Let's see, contains all the accumulation point. In other words, for any sequence in E that converges to x naught has to be part of E. So I can picture a collection of points in this set. Let's say this is x1, x2. I'm going to pick a sequence that say converges to a point on the boundary here. So this will be the limit, okay? So we have a sequence that converges to this limit x naught. So x naught has to be E, okay? This point has to be part of E. That means that'll imply this guy is a closed set. Okay, it's closed. A different example will be we remove the boundary here. We pick something. So this is the set E, okay? Set E is everything inside. And notice that for a sequence, so this x1, x2, for a sequence like that, that eventually, let's say, converges some point on the boundary here. So this is my x naught. And notice this x naught is not part of E. Okay, it's not part of E. And that's why this guy is not closed. Okay, that's why this guy is not closed. And this guy is an open set. All right. So once again, this is an algebraic statement down here. But this is a topological statement. It has something to do with the structure. A set is closed if and only if it contains all its accumulation point. Okay, accumulation point. So think about that one. And let me see. This is the end of 9.1. Okay, 9.1. In the textbook, they call accumulation point the limit point. All right. I know you probably can't see it, but this is a 9.8. They call it accumulation point. And there are some simple exercises that you can work on at the end of a 9.1. All right, but that's the end of sequences in Rn. Okay, our next topic will be limits of functions in Rn and continuity of functions in Rn, followed by the derivatives and the usual stuff. That's it for this.